Okay. OK， 好的。OK， 这边好。OK。Okay, let's get started. Okay. So first thing, just want to remind you, the project number 2 has been uploaded to the EE class. Okay. So please check it out. Okay. And it's also about time that you guys, remember I told you like the final project. For the final project, like 2 small groups will be combined to form a large one, right? I mean, so it is about time that you need to decide like which small group, like your group, would like to collaborate with for the final project. I will have the TA to prepare the form to collect that information from you. Okay, hopefully like before probably before the due date of the second project. Okay, should be reasonable. Okay, because the final project actually will be announced like in another few weeks. It will actually be announced earlier than the third project, okay? Because the final project is supposed to be bigger one, and I expect like there will be collaboration between groups, okay, to work on the final project to make it better, okay? So, okay, come back to the lecture, okay? I hope to be able to finish this chapter in 2 weeks, and then we will move on to the CNN. Any question? 有什么问题吗？就开始了。开始。对。Okay. So last week we talked about an important finding. Okay, an important finding that like if you use the sigmoid or hypertension type of activation along with the random initialization with like the normal distribution with mean 0, variation 1, okay, standard deviation 1, I'm sorry. Then what happens is that, okay, in the back propagation, the variance, okay, is going to become bigger and bigger, which is the very important reason to contribute to the vanishing gradient problem, right? So the Xavier, okay, or Gorod, okay, Xavier Gorod and Yosha Bengio, okay, in their paper, okay, they prove this is the reason. In addition, okay, in this paper they actually propose an initialization which if you use it along with the sigmoid, okay, activation function, then you can avoid this type of phenomenon, okay. Of course, in fact, it's not possible to guarantee, okay, both, this phenomenon from happening, okay, unless the layer has an equal number of input and, inputs and the output, okay. We call that as fan in and the fan out of the layer, okay. So what do we mean by fan in, fan out? Because for each layer, say this is a layer, each neuron has some connection to the previous layers, right? To the neuron in the previous layer. We call this number, the number of connection for this neuron, as fan in. And the fan out is the number of connection from this neuron to the neuron in the next layer. So this is for the fan out. Okay? So basically, okay, if fan in and the fan out are the same, okay, they prove that we can avoid this variance, increasing issue, okay, by using a special initialization, okay. But if we know we at each level, at each layer, we may use different number of neurons, right? It's very common. So the fan in and fan out in many cases are different, okay. So we cannot completely avoid this, but they still derive approximation, okay, saying, okay, if you, even if the fan in and fan out are different, if you use this initialization, the chance for this variation to increase, layer by layer, okay, is going to be, reduced, okay. They call this Xavier initialization or Goro initialization. Okay, Xavier and Goro, it's basically it's the name of the first author. Okay, so what exactly is that? Okay, it's like this. If you use a logistic activation function, which basically is a sigmoid, okay, then that fan average to be the average of the fan in and fan out. Here, of course, we are talking about the approximation, okay, in the case that fan in and fan out values are different, okay. And if you want to use normal distribution to randomly initialize the weights, then, okay, you should use mean zero and the standard deviation like this. The square of the standard deviation to be like a fan average, 1 over fan average, okay? Or if you are using a uniform distribution to randomly initialize your weights, then your value should be in between negative R to positive R, where R is this one. Okay, so they say if you use this way to initialize your weight, okay, randomly, then you can tell this is what should I say? It is still random initialization. It's just the range. The range for this random initialization is different. It's different, and by this very small tweak, they prove that the chance for this increasing variance issue, okay, will be alleviated. Be careful, I'm saying alleviated. I didn't say completely gone, okay? Because as I say, if you want it to be gone completely, okay, your fan in, fan out value has to be exactly the same. But when we design neural network, a lot of time, I mean, we have different number of neurons between layers. So it is, not very common for fan in, fan out to have the same value anyway, okay? So, this is something interesting, okay? I want to tell you. Remember, I keep telling you, I tell you like Yang LeChong is kind of like a god, right? I mean, you may wonder why I keep saying that. I mean, well, Yang LeChong and Yoshio Bengio, I mean, three of them like received like turing award together, so they should have equal contribution to this AI, technology. Yes, I mean, if you say that, that's true. But Yang LeChong is a kind of a special person who has a very, what should I say, like who has a vision. Like he can see something that will happen like many years later. For example, here, if you replace fan average with fan in normal distribution equation, you get an initialization strategy that Yang LeChong proposed in 1990s. 1990s. When was this Xavier initialization being proposed? This was proposed after 2000, after year 2000. Okay, they found out this after year 2000, but Yang LeChong identified this 10 years earlier than anyone. But he didn't prove it. He just found that, oh, if I do this, well, the neural network training will improve a lot. But he has this guts intuition to say, okay, we should do this initialization. So you can see that, okay, in 1990s, he called this LeChong initialization. So back to like more than 10 years ago, he already envisioned such initialization, okay, even without very concrete proof. Okay, he did some proving, but not very through proof. Of course, the real proof, okay, was done actually by this paper, the Bengio's paper. Okay, so so that's why I keep telling you, okay, this Yang LeChong is really special, really special. Okay. And later on, okay, Gilenvide, okay, and Klaus Robert Mueller, okay, they published a book in 1998, okay, about neural networks, okay, tricks of the trade, okay, and that book include Yang LeChong's initialization technique. And that book actually like recommend Yang LeChong's initialization. So Yang LeChong's initialization was known, okay, at least by a small number of researchers back to like early days, but it was just like nobody. Yang LeChong was not that. Not a big name, okay. Or let me put it this way, okay. Not a big name, okay. Back to early 1990s. That is why, okay, his finding was not that well known, okay. So if he was a big name professor, maybe like the AI advancement will occur maybe like 10 years earlier, okay. So this is why I keep telling you, okay, Yang LeChong is really something else, okay. So it took over a decade for researchers to realize how important this trick is, okay. So they will use Glorot initialization, okay. This initialization not only speed up the training, okay, it is one of the tricks that led to the success of deep learning. Okay, without this, as I said, no, the reason the second AI wave died was because everybody know, okay, we should have multi layers, but the training for a deep neural network was so difficult without these small tricks. Okay, so these small tricks, okay, are very, very important. Okay, so what happened? So some papers, they provide similar strategies for different activation functions, because as we know, in the old days, people use a sigmoid, okay, but recently more and more people use ReRU, right, and variant of ReRU. I mean, as I will explain today later, okay. So so for different activation function, obviously you should have different initialization strategy. Okay, so they will show you. Okay, let me show you a table. Okay, that lists the initialization techniques that you should understand. Okay, so for example, if you use no initialization or hypertension or logistic softmax, okay, this type of saturated activation function, then you should use Gorod or Xavier. Okay, if you use ReRU or a variant, okay, what are these variants stand for? Okay, I will explain later. Okay, so you should use the He initialization. Okay, and which said is a normal distribution with sigma squared to be 2 over fan in. Okay, by the way, He is obviously a Chinese name. Okay, this is a Chinese guy who made also very strong contribution to AI research, because obviously we use ReRU a lot. In the recent years. Okay, and Yang Lechong. Okay. If you use CRU, okay, you should use the Chong initialization, which is 1 over fan in. But so you may wonder what is CRU? Okay, it's I'll explain this activation function later on. Okay, so basically, for different activation functions, you should use different initialization, weight initialization strategy. So here, okay, is how you write your program in Keras to use different initialization strategy. If by default, Keras use Gorod or Xavier initialization with uniform distribution, okay? But if when creating a layer, if you want to change to He initialization, because we use ReRU all the time, right? So you can do something like this, okay? Setting kernel initializer equal to He uniform, okay, or kernel initializer equal to He normal, something like this, okay, or in this line, okay, chaos.layer.dense, okay, you create 10 neurons with ReRU activation, and the kernel initializer equal to He normal. This is for He normal. If you want to use a different distribution, such as a uniform distribution, you can use He uniform, obviously. Okay, so if you want He initialization with a uniform distribution, but you want it to base on fan average, but not fan in, then what happens you can write a program like this. He average INIT. This is just a name, okay, a variable name, okay. It's that take object that you create by, from the Keras.initializers variance scaling, variance scaling. This one create a initializer for you, okay, and and you need to tell it that what scale it is, and the mode, what mode it is, and what distribution it is, Okay, as long as you tell it like correct, like information, it will create an initializer object. Okay, here, and when you create a layer, you can assign this initializer. Okay, just like what we have earlier. Okay, so that's pretty much about it. Okay, so then it's like activation functions. Okay, so remember like this vanishing gradient issue. Okay, was caused. Okay, the variance keep going up and up, and eventually the gradient vanish. It was because like we have a saturated activation function, right? So when I say saturating activation function, I mean like when the value is either too big or too small, the derivative is almost flat, right? So yeah. So obviously the choice of activation function in the old day also contribute to this vanishing gradient issue. Okay, so as a result, the sigmoid activation function, okay, I mean which was used very often, okay, in the early day, because everybody believed like it's a gut like a choice to use a sigmoid in biological neurons. So why not we use the same thing for the artificial neural network? Okay, but it turns out to be not true. Okay, but anyway, so everybody start to switch to other activation function. Obviously, one of the good choice will be ReLU, right? But ReLU also has its issue. Okay, ReLU also has its issue because we know ReLU is like when the input is greater than 0, okay, it is linear, right? But when the input is smaller than 0, you get a flat line, right? It's 0 basically, right? So so ReLU activation function is not perfect. Okay, it still suffers from problem known as dying ReLU. So this is also a name, okay, that is well known. Okay, it's an issue that is well known. Okay, what is dying ReLU? Okay, it's like this. During training, some neurons effectively die. Okay, meaning they stop outputting anything other than zero. So in some cases, you may find that half of your network's neurons are dead, especially if you use a large learning rate. Okay, so during training, let's stop here. Okay, so about half of neurons will be dead. Why is that? Well, assuming, because for ReLU we know like we are going to get like a weighted sum from all those inputs, right, of this neuron before we apply ReLU, right? Okay, assuming this weighted sum has the same, has a very flat distribution. Okay, very uniform distribution across like all the values. Then think about this. Okay, you get half of the chance for a neuron, okay, to get a negative like a weighted sum, right? Because for real line, you have a half of a real line to be positive and half of a real line to be negative, right? So assuming you can get any value from this weighted sum, then on average you have 50% of the chance that this weighted sum turn out to be smaller than 0, right? If it's smaller than 0, the rerule, when you apply the rerule, okay, you get 0, right? You get 0. Okay. So that is why, okay, about half of the neurons may die. Okay. Statistically, this is very natural, right? Very natural. But it will, but the issue is, so during training, if a neuron's weights get updated, such that the weighted sum of the neurons input is negative, it will start outputting 0. So that's exactly what I just mentioned. Okay, then we know about that. Okay, and this contribute to like a half of neuron will be dead. Okay, part of the reason. But when this happens, the neurons is unlikely to come back to life, since the gradient of the rerule function is 0 when its input is negative. So because we know the shape of rerule is like this, right? Here it's flat. So when you are here, you don't have gradient to move. Okay, you don't have a gradient to move. You may argue, okay, yeah, I mean we got this weighted sum like this to be negative this time, but in the next round maybe we are not going to get a negative from this weighted sum anymore, right? But keep in mind, okay, so if this is a neuron, okay, it receives value from the lower layers. Okay, if it's negative, if this weighted sum is negative, okay, and assume like half of the neurons in the next layer is negative 2. So half of this neuron will output 0, right? Okay, because we use rerule all the way, right? I mean for all the layers. So half of these neurons may output 0 as well. So the chance for the rest of the half of the neurons in the previous layer to output something that help you to escape from this negative weighted sum, okay, it's not that high. It's not necessarily very high, okay. So a lot of time, okay, when you get a negative value, you will stay there, okay. So the neuron is unlikely to come back to life, okay, and we have this dying rerule. I'm not saying this dying rerule happens like all the time, but yeah, it is an issue that we need to consider. Okay. So to solve this problem, okay, you want to use a variant of rerule function. Okay. A famous family of the variant is called the leaky rerule. Okay, what is leaky rerule? Leaky rerule is defined as like this. Leaky rerule, okay, alpha z. Okay, z is the input. Okay, weighted sum. Okay, it's a max of alpha z. Okay, and this alpha is normally a small number, small positive number. So the leaky rerule, okay, the shape, okay, is going to be, because this alpha, as I say, it's a small positive number, okay, maybe 0.001, okay, something like that, okay. So if z is positive, obviously z is greater than alpha z, right? If z is positive, okay, then obviously z is greater than alpha z, because alpha is a value smaller than 1, right? Okay, so when the input is greater than 1 than 0, okay, you get it's going to be the same as the ReLU, okay? But when z is smaller than 0, okay, then what happens is that alpha z is bigger than z. So it's going to be something like this. This is the shape of leaky ReLU. Okay, when the weighted sum is greater than 0, well, it's a same linear function. But when the weighted sum is lower than 0, it is also a linear function, but it has a very small slope, very small slope. This slope equal to this alpha. Okay, and this one, okay, this phenomenon, okay, is considered as leaky. Okay, as leaky. So this is why this function gets the name leaky ReLU. Okay, so what is the advantage of leaky ReLU over ReLU? You can see obviously, okay, yeah, when the weighted sum is negative, if you use leaky ReLU, you still get a gradient, right? Even though the gradient may be small, because this alpha value is a very, very small positive number. So yeah, I mean, so your gradient is small, but that's fine, because eventually, okay, even if you have a small gradient, this small gradient eventually can help you, recover from the dead status. Okay, so this small slope, small gradient is very important. So this alpha is typically said to be 0.01. Sometimes it can be, different value, but it's always like a small positive value, basically. Okay, so you can, your leaky ReLU never die. They may go into long coma. Okay, coma just means like it's 晕倒. Okay, faint. Okay, but eventually they will have a chance to wake up. Okay, so there are actually many variants of the ReLU function. Okay, here we are going to talk about several of them. Okay, a recent paper compares several variants of ReLU activation function, and one of its conclusions was the leaky variant always outperformed the strict ReLU activation function. So you can see that ReLU, okay, if you want to use ReLU, okay, you may as well use leaky ReLU. Okay, so in fact, setting alpha to be 0.2, a larger leak will result in better performance than a small leak, such as 0.01. Okay, so this paper tells you, okay, a larger leak sometimes will get a better performance than the small alpha value. Okay, and they also evaluate other variant of ReLU activation function, such as random leaky ReLU. So what is random leaky ReLU? Okay, it's abbreviated as ReLU. Okay, where alpha is picked randomly in a given range during training. So ReLU, in this random ReLU, random leaky ReLU, okay, alpha is maybe picked between 0 and 1. Okay, as a random number. Okay, in every iteration. In every iteration. Okay, but of course that's for like training. Okay, and it is fixed to an average value during testing. Okay, so in the testing, okay, if so let's say if the range is between 0 and 1, then during testing you may set it to be 0.5. okay, as average value, okay. So it also performed fairly well and seemed to act as a regularizer, okay. So the randomized leaky ReLU, okay, can also help you to fight with overfitting. Okay, so this is a very good. It has a very good, property. Okay. So another one. Okay, there's another variant called parametric leaky ReLU, p-ReLU. Okay, where alpha is authorized to be learned during training. So alpha is one additional learnable variable parameter, learnable parameter in the network. Okay, so it can be modified by backpropagation. Okay, like any other parameters. Okay, so this parametric leaky ReLU, okay, is something like this. So it becomes this was reported to strongly outperform ReLU on large image data set. So if your data set is huge, p-ReLU is has a very good performance. Okay, but now because obviously you increase the number of parameters, right? When you increase the number of parameters, it means you increase the complexity of the model, right? So if your data set is not large enough, you run the risk to overfit the model, okay? Because when I say, what happens when the model overfit? Okay, your model is too complicated. Okay, it captures a small variation of your. We should only capture the trend of the data, but it captures a small variation of the data set, which causes the overfitting, right? So in some sense, this p-ReLU and the r-ReLU are opposite to each other. Okay, but both perform better. Both actually perform better than ReLU. Okay, but the r-ReLU help you to fight with overfitting. p-ReLU, okay, may cause overfitting. So which one to use? Okay, so this is leaky ReLU, as I said. You have a small gradient here. Okay. Which ReLU to use? Okay, we are going to talk about this. Okay, very quick. In the next slide. Okay, so here, okay, we would like to introduce one more variation of ReLU. Okay, so there's a paper, okay, published in 2015. Okay, that proposed a new activation function called exponential linear unit, or abbreviated as ELU. This ELU was, it outperformed all the ReLU variants in their experiments. Okay, the training was reduced, and the neural network performed better on the test set. Okay, so what is this ELU? ELU looks like this. When the z greater than 0, greater or equal to 0, it's just z. So it's when the z is greater than 0, it's the same as ReLU. But when z is smaller than 0, it's something like this. It's alpha times this expz minus 1. This alpha value, okay, is adjustable, but a lot of time we set it to be 1. Okay, we set it to be 1. So it looks like this. When the weighted sum is smaller than 0, okay, eventually it's going to get like as close to -1 as possible. Okay, but here, okay, the shape is slightly different. So So it takes a negative value when z is smaller than, so which allows you to have an average output closer to 0. Okay, so remember I told you like one of the reason this sigmoid activation function create like will increase the variance. Okay, I mean it's because its average is going to be 0.5. Remember I told you about this. The average is 0.5. So the output, okay, the output of of the average is 0.5. So you can see that, okay, if you initialize starting from like the average is 0, start from 0, so it's going to increase the output, right? So because the average, this one is 0, this one is 1, right? So the average is 0.5. And the similar problem happened for the ReLU, right? So no matter it's a ReLU or leaky ReLU, if you consider the average, it's going to be much larger, right? So it is also possible to make the variance to increase. But if we consider the EOU, yeah, this part is positive, but this part, now we get negative values, right? So these negative values help to cancel out some of these large positive value. So the average is no longer that big. Okay, we are able to pull the average back a little bit. So this one help you to a little bit in in the direction of reducing the variance. Okay, for each layer by layer. Okay, and also, okay, it has a non-zero gradient when your weighted sum is smaller than 0. Okay, so which avoid the dying ReLU, right? And the function is also smooth everywhere. Okay, originally for the ReLU, we know like when z is 0, it's a turning. That point is a turning point. It is non-differentiable. But the EOU, okay, this place is differentiable, so which is nice. Okay, you don't have that issue. Okay, so it does not bounce as much left and the right when you close to when the weighted sum is close to 0. Okay, so there are so many advantages, okay, for EOU. So what is the drawback? What is the drawback? There's no, well, not too many. Okay, free lunch anyway. Okay, so main drawback of the EOU activation function is that it is slower to compute than the ReLU and its variant, because no matter which ReLU variant that we talk about, okay, ReLU, leaky ReLU, P ReLU, R ReLU, okay, they are all linear function, right? Linear function. No matter it's z is greater than 0 or z is smaller than 0, okay, basically it's a linear function, right? So linear functions obviously are much fast to compute, right? Okay, but this EOU, okay, because when z is smaller than 0, okay, this one requires you to compute exponential value. It takes longer time to compute this part. Okay, so it is it is like the disadvantage of this activation function. Okay, so during training, this is compensated by faster convergence rate. So if you use EOU, yeah, it takes longer time to compute, but maybe, okay, if you use EOU, originally maybe you require like let's say 100 epochs, 100 iterations to train a neural network. But if you use EOU, maybe you only need 20. So even though for each iteration it takes more time, but it's the total training time is reduced. Okay. So however, at test time, an EOU network will be slower than ReLU network. So if you use EOU network to do inference after the training, okay, it is going to be slower after all because it takes more time to compute this activation function. Okay. So now we have we arrived like the place to introduce the CRU. Okay, it is called scaled EOU. So it's a variant of EOU function. Okay, it's a scaled variant of EOU activation function. So this paper, okay. So what is important about this CRU activation function? This CRU activation function, okay, has a very nice property. Okay. If all hidden layers use CRU activation function, then the network will self-normalize. What does that mean? It means if your input is normalized, okay, and it goes through like a CRU layer, okay, it guarantees that the output will stay normalized, okay, with with a average 0 and a variance 1 maybe. So a standard deviation 1, okay, during training. So it's a very nice, okay, because it completely, solve the issue of that, the increasing variance problem, okay. So so which solve the vanishing exploding gradient problem, okay. So as a result, the CRU activation function often significantly outperforms other activation functions for such neural networks, okay, especially deep ones. So there are, however, a few conditions for self-normalization to happen. So if you want to use CRU, okay, you need to make sure, okay, this property, okay, these conditions are met, okay. The first one, the input features must be standardized, okay. So you have to, first normalize your input in order to guarantee its output will be normalized, okay. The input obviously has to be normalized first. And second, every hidden layer's weight must be initialized with the Chong normal initialization. So you just need to follow the Chong initialization, okay. So just set the kernel initializer to be the Chong normal. This is very easy, okay. The third one, the network architecture must be sequential, okay. You can only have one path. So for example, for non-sequential architecture, such as recurrent neural networks, okay, because recurrent neural network has like feedback mechanism, so it is not sequential. It is not sequential. Or remember we talked about the skip connection, okay, in the wide and deep neural network. Remember we talked about that, right? So that skip connection, okay, make the model, okay, not sequential. So if your model is not sequential, okay, something like RNN or something like this, you have skip connection, then CRU will not necessarily outperform other activation functions, okay, because CRU doesn't guarantee self-normalization anymore, okay, in non-sequential function, okay. And one last thing, the paper only guarantees self-normalization if all layers are dense, but some researchers have noted that CRU activation function also improve performance in CNN. Okay, so in CNN you can also use C-rule. Okay, you can also use C-rule. Yeah, we are going to talk about CNN next chapter. Okay, so just for your information. So now, okay, we have so many different activation function, right? In addition to sigmoid, hypertension, logistic, okay, those old ones. Now we have ReRule, leaky ReRule, P ReRule, R ReRule, ELU, C-rule. So which one to use? Which one is better in what condition? So we are going to talk about that. Okay. Well, let's take 10 minutes break. Okay. After that, let's talk about this.